All right, hello everyone. So today we're going to finish up our unit optimization. So the thing we were talking about last time was gradient descent, which is our algorithm that we can use when to find a local minimum when we can't solve a problem analytically like we did with RSS. So the idea behind gradient descent is you start with an initial guess and you take steps downhill on the cost surface, always proceeding in the steepest downhill direction, and you use a small enough step size that you don't overshoot. And if you go too far, you could actually end up going past the low point and go up and get even to a place worse than when you started. So you take downhill steps with a small enough size, and you just keep repeating that procedure, and eventually you will get down to the point where the gradient equals 0 and you find your minimum there. So that's the idea. So alpha is our step size or learning rate. It is something you could use a different step size at every iteration, so we'll talk about that today. And we said that one thing about this is that if there are multiple minima in your cost surface, some are worse, some are better, then you may not get to the lowest one overall. So that's one of the issues with this. However, as we'll talk about later today, if you have a convex cost, then all the local minima are equally good. All right, so the other thing we did last time was we sort of proved to ourselves that this is really going to work. We applied this Taylor series approximation, and we saw that the step size, if the step size is small enough, we will make progress on every iteration. Okay, so let's see what else we did. We applied this idea to our cross entropy loss, this one. So we had to kind of be clever in doing this. We had to think about decomposing this into two steps, a linear transform and a separable function. So this is something that happens a lot. You'll see this on other homework problems, lab, and so on. And the other thing we did was we implemented this. And when we ran it, we tried different step sizes. And we saw a behavior that's sort of what we would expect or learning rates, step sizes, same thing. If we start with a very small learning rate here, then you can see that the progress is pretty slow. The loss decreases slowly with the iterations. If we increase our learning rate, we can speed things up. However, if we increase it more, then we start to get into the situation where sometimes we overshoot and things actually get worse. In this case, overall, even though we were sometimes overshooting, sometimes we'd make a lot of progress, and this seemed like the best step size. If we tried to increase it even more, then things got much worse. Like things were much less consistent, and in fact, we never seemed we were converging to any value. We were just overshooting back and forth over where we wanted to a minimum. So this kind of brings up the importance of choosing your learning rate, and so that's sort of the next topic of discussion is describe one algorithm out of many that are out there that try to do this. They try to adapt that step size and learning rate at every iteration in a way that will still guarantee convergence, but hopefully will work faster than a fixed step size that you might guess and try. So to understand what's going on here, this is the analysis result that we derived before. So if you remember, we said this is the cost at the new iteration after we perform the kth step. This is the cost previously. This is a component that helps us. This is going to be a negative component that decreases our cost. Over here, we have a positive component that makes things worse. This potentially increases our cost. And so what we said before is when alpha k is small enough, this term will overwhelm this term and we will make progress. So that's sort of the starting point, is to remember this decomposition. And this is what's known as the Armijo rule. This is what you do at every step k. Let's say you have some step size alpha k. What you do is you check to see if this condition is satisfied. So this condition looks very much, or let's say the right side of this looks very much like the first two terms here, except that there is another parameter c, which is some number between 0 and 1. And for example, we can just imagine choosing that number as 0.5. It's something that's hard to optimize, so you tend to just choose a value like 0.5. Okay, and so what you do is you check to see, is this, so you can, given your step size alpha k, you can perform a gradient descent step and you will get this. You can also take your old cost and subtract this quantity, and now you can check to see, is this greater or equal to this? If so, that's good. Your cost is guaranteed to decrease, and I'll explain a little bit more on the next slide. However, if that fails, that means you're not going to accept that step. You're not going to accept that choice of step size. You're going to try again with a more conservative step size. So here's the update down here. So if that rule above passes, you accept the step, you accept that new WK plus 1, and you set your new step size. And actually, yeah, so what you do here is not only do you accept that step, but you say, maybe I can be even more aggressive next time. Maybe my step size is too low. Yes, it worked, but I'm gonna push it. So what you do is you take your old step size and you multiply it by some number greater than 1. And the next iteration, you will use this new step size, which is even more aggressive. Okay. On the other hand, if this rule over here, or this criteria was not satisfied, then you throw away that update and you try again with an alpha k that is some number smaller than the previous one. So beta decrease is some number less than 1. So you be more conservative. Okay, so this is what you do at every iteration. Okay, so let's take a look at this. This picture sort of illustrates what's going on. So this is the equation that we started with. This is the result of our analysis, where we have old cost, a decreasing term, and an increasing term. And overall, this gives us the cost we would have obtained at the new update for this particular step size, alpha k. So in this plot, that's this red curve. So overall, you see that the red curve has sort of a quadratic sort of shape. So if you remember, when alpha k is small, we know that this term is much larger in magnitude than this term, and we get some decrease overall. So that's sort of what's happening over here at the beginning. This red function is decreasing as alpha k, it's decreasing. But if you make alpha k too big, then we said this term can actually overwhelm this. And so that eventually happens over here. So eventually, this term is overwhelming it, and in fact over here, you would make negative progress. Okay, so this is showing this function here as a function of alpha k. So a couple landmarks would be if we set, okay, let's make a definition. So we're going to define this right side, and actually notice that here we have the that C number. This is the term that's in the Armijo rule. It has that C there. So this is what we're looking to verify, whether the left thing here is less than or equal to this. Okay, so to understand what role this is playing, if you put in C equals 1, you just get this part, right? That would just be, so that's like essentially, it's this over here. This is saying you have a purely linear approximation of your true function, right? If you ignore this altogether, this is just the linear approximation of J at the point WK. So if I do a linear approximation of this red line, red curve right here, it's just going to be, it's going to match it in slope perfectly there, but then just keep continuing. So that's what this function, if you put in C is 1, you get that. So you can see it's J hat 1. Now, we said on the previous page, choose C somewhere between 0 and 1. So imagine what happens when C is 0.5. That's this blue line. You can see how it's just half of whatever slope this is. So that's the blue line. So the Armijo rule says whenever the red curve is less than or equal to that blue line, accept the step. So when the red curve is under the blue line, that happens for all the alpha k's in this range. Right? If alpha k is beyond this point, then the red curve is above the blue. This Armijo rule would fail, and you would reject the step. Okay. Is this starting to make sense with the picture? So you can see that this is sort of like an upper bound on the actual function that holds for a reasonably small set of alpha k. And you can see the good thing is if you accept any of those alpha k's, you will be doing pretty good. You will be, your cost will be somewhere between here and here. And by rejecting those very large values of alpha k, you protect yourself from your cost increasing. So it's a little bit of a, it's not exactly clear how to choose C, but in practice, I don't know that it matters that much. You just choose a value like 0.5, and this overall procedure works pretty well. Okay. So that's sort of explaining what's happening here. So you can probably visualize, let's say you chose C as 0.75. No, let's do a really small C, like a C of 0.1. In that case, you get something like this, right? Now you can see what's not great about that is you're allowing a very wide range of alphas that could do significant overshooting. On the other hand, you could say, well, what happens if I choose a C of 0.9? Well, if it's 0.9, it's going to be something like this. And now that's not ideal because you're only including those C's, and you're maybe not making all that much progress. So if you go to 0.5, this is sort of like a nice midpoint. But you never know exactly what shape this has. Well, I mean, so this, maybe I'll stop there and see if there's any questions. Is this making sense? Yes.
I have a question on the previous page.
Sure.
So in case that the rule fails,
Uh-huh.
if we're recalculating omega k plus 1, wouldn't we want to set alpha k to the new value instead of calculating alpha k plus 1? Isn't that for the next step?
Yeah, it's kind of like sort of a matter of definition. So the way that I described it here, k is really just always moving along. You never redo a k. But what you do is if the step fails, you assign wk plus 1 at wk. Does that make sense? So it's like It's like you're going to evaluate, you're going to output a value of W at every K. Anytime it fails, you just repeat the last W. So it's sort of just a matter of definition. We're talking about doing the same thing. And that way, the alpha K plus 1 is the one I'm going to use to try again to get a better, an admissible W. Yeah, so this is a little bit easier to code because you can have a for loop over like a fixed number of steps. Let's say you want to do 1,000 steps. So now this is going to do 1,000 steps. Some of them might be kind of failed steps in the sense of optimizing, but they're useful in the sense of like finding a good alpha that will make the later steps more productive. Otherwise, if you had a for loop and this kept failing, it's like you would be stuck at the same K in your for loop, but this thing would be running, and you wouldn't ever know whether it's going to stop. Maybe you keep decreasing your step size over and over. So it's just they're slightly different in terms of the implementation, but okay. Yeah, so that's the approach. Maybe to put things in perspective, you could say, well, there's other things we could do. For example, why don't I just try a bunch of alpha Ks? So let's say I try a bunch of these alpha Ks and I evaluate all these points, and then I just choose the best one, which in this case would be this one. That's certainly something you could do, and that's what I'm alluding to down here. But the problem with that is that when you think about what goes into evaluating each of these, it takes a certain amount of computation. You actually have to do the full gradient descent update for each one of those alphas, right? So the nice thing about the Armijo rule is that it's very inexpensive. So yes, the alpha K you get is not perfect, but it's very fast. It doesn't really take a lot of extra computation to get this. It doesn't take a lot of extra computation to do it. Okay, so there are alternatives, but the Armijo one is just a very famous one. It's used quite a bit, and there are definitely other approaches to adapting the step size. So this is just one of the most well-known approaches. Okay. Yes.
So the ideal alpha K is the minimum of the red line?
Yes, if you could, at every iteration, you would choose the ideal alpha K right here.
But we don't know the equation for the red lines, that's why we don't just minimize it?
So,
or is it difficult to minimize it?
Well, it's the cost at the new W. So remember, in order to compute the cost, we programmed, where is it? Like this, right? So this is how we would be computing the cost. So for every one of those test alphas, you would run this code again. So let's say I computed 10 test alphas. That's kind of the equivalent of computing 10 steps.
Yeah.
I could have made a lot of progress in 10 steps, but here I'm like trying to be really picky about this one step. That's not so efficient. So the Armijo rule is kind of rough, but it's efficient. So basically like depending on how you set all these different parameters, like you'll have a few failed steps as you go, and not all your alphas will be optimal, but eventually you will learn sort of to put alpha in a certain range, and it will kind of converge to a certain range of alphas, and then we'll see a plot, and it kind of hones in there. Okay, so all right, so that's I think I described everything here. So yeah, the cost is guaranteed to decrease. So that's or I guess there's a special case if the gradient is exactly 0, you're already at the minimum, and there's nothing to decrease. But the cost is guaranteed to decrease, and how much does it decrease? By a fraction C of that predicted by this linear approximation, just by the very first part here. So this is an overestimate of what you can get, right? Because this one is lower bounding us, because it's not including this term. So this is too optimistic for what you can actually get. So here you're settling for some fraction of this overly optimistic estimate. Okay, so we talked about all this. In terms of these beta parameters, you have to choose these ones too. So in practice, usually you make beta increase maybe around, I like to use 1.1. So it's just like a 10% increase. You get a little bit more aggressive, but not a lot. On the other hand, when things are failing, you want to make a correction, because if things keep failing, you're just wasting steps. The steps are not doing anything for you. So I like to set beta decrease as something like 0.5. So that's a significant reduction when you fail, and then you gradually increase. Significant reduction, gradually increase. Okay, so yeah, so that's the method. Any questions on this? Okay. So in Python, here's the code. It's pretty easy. So we have an outer loop over the number of iterations. And here's where we take our gradient step. So here's where we take the step based on the previously computed gradient, and here's where we reevaluate the gradient and the lost at the new step. And here's where we do our check to see if our MIHO condition is satisfied. Here's our value of C, the learning rate. And this is just the norm of the gradient squared. And here you can see if the step is successful, we update it. In other words, this temporary value for W1 is then loaded into W0, which is like our final value. The temporary cost is loaded into the final cost. And the temporary gradient is loaded into the final gradient. Finally, we increase our learning rate by a little bit. On the other hand, if it fails, all these temporary values are basically, they go unused. We decrease our learning rate, and we try again. We will again use the same gradient we used before, but now with a more conservative learning rate, get our temporary values, see if they worked or not. If so, we keep them as final values and so on. And if they fail again, which is a possibility, we will just decrease our learning rate again and try again and again until we finally succeed. So this is what happens when we do it. On the left, we're looking at the loss versus the iteration. And you can see that things are never increasing. Things do go down. You can see that there were some iterations where it looks like things stayed the same. Here, maybe it took us a while. Maybe we started out with too large of an initial guess, and it took us a while, but not that long. This is on a log scale, so this is iteration 1, 2, 3. So it took us, from our initial guess, like 2 or 3 iterations to finally find a value that satisfied your MIHO rule, and then we started to make progress. Here's the learning rate versus iteration, is what we started with. Then we decreased it to 0.5. Then we decreased it again to 0.25 of the initial value. And then we started to make progress. So gradually we're increasing it. And all throughout, their MIHO condition was being satisfied. So even though these learning rates at the beginning failed us, they seem to be working fine here. But then they started failing, so we reset again, and so on and so on. And what you notice that's sort of interesting is that eventually we're sort of converging to a learning rate around here. Whereas when we started, we had to use a more conservative learning rate. So this is sort of reflecting the shape of the cost surface. So when we started, the steepness was just different than when we were converging at the true minimum. So, it's hard to find one step size that works really well in all cases, but the Armijo rule is able to dynamically adjust the step size so that it works well as you go through these different regions of the cost surface. Okay, and the final loss is actually better than what we were able to obtain with any of the previous fixed alphas, and the test accuracy, I think, is also better. Okay, so that's the Armijo rule. Any questions or anything here? Yes.
Like for the learning rate, would it be like taking the first and when it comes to an end, it gets smaller?
Well, in this case, you can see, no, it actually, we started here and it ended up a little bigger.
So why does it happen?
It just depends on the shape of the cost surface. So basically, like like the steeper the cost surface, you have to be more conservative with how far you move, because when the cost surface is very steep, you can easily overshoot. But when the cost is very shallow, you want to move far.
It's like shallow at the.
So here it was a little shallower at the end than the beginning.
I can
So-
see that.
Yeah. So but that's not universal. It just depends on the problem.
Okay.
Yeah. Okay, any other questions on Armijo? Okay, great. Yeah.
You go to the bottom right, is that, when you call predicts, is that, like, can you put that in the class that you made earlier in the slides?
Let me think. So in the class we made earlier, we were just trying to optimize W. So we're doing classification here. So once we have the W and we want to, we're getting our labels here. I don't remember exactly how this was constructed, but this is sort of something different. So for linear classification, we take our test features, that's a matrix. We take our W vector, and we multiply x on the right by W. We now get a column vector of class Z's scores, or test scores. And then the last thing we do is we quantize them either to 1 or 0. So the predict function is essentially doing a matrix vector multiplication followed by a quantization to 0 and 1. That's all. Yeah, you can look at the demo code to see exactly how that was defined, but I don't remember exactly. Okay, so, all right, any other questions? Okay, great. So, so we've been talking a little bit about convexity. Convexity is important because when something is convex, we can use a technique like gradient descent and not worry about it converging to a bad local minimum. We always know it goes to a global minimum. So let's understand a little bit more about, what is this convexity stuff. So to describe it, we first have to talk about convex sets, and then we can talk about convex functions later. So a set is convex if for any, we'll call the set D, if for any 2 points in the set, if the line segment between those 2 points is contained within D. Okay, so the way you can build a line segment is you take a number anywhere between, in the interval between 0 and 1, and you do sort of a weighted average, sometimes this is called a convex combination, of those 2 points. So if this is x and y, for different t's, for small t, I'll be over here, and then as t goes more and more to 1, I'll be over here. So what I need is that all the points on this line segment are inside my set D. And I need that to hold for every x and y. So like here, no matter how I construct x and y inside the set, you can see the line segment will be contained in the set. Here, in some cases, the line segment will be contained, but in other cases, it won't. This line segment goes outside the set. So this is a convex set. This is a non-convex set. So examples of convex sets, circles are convex, squares, ellipses. If you look at the Rn, which is the space of n-dimensional arrays of real numbers, that is a convex, that's a convex set. If you look at a hyperplane in Rn, that's convex. If you look at a half space, like let's say you look at all n-length vectors where the first element is non-negative. So that would be, it'd be like a half space of the entire Rn. So that's also convex. There's many convex sets like this. So a lot of what we work with. We usually work with Rn in terms of optimizing parameters, right? We're just optimizing, or RD, we've been calling it. Okay, so that's convex sets. Now convex functions. Function is convex if two things. First of all, its domain is a convex set. And second, if this condition holds. So we can explain this condition as if you apply a convex combination on the input of the function, that should be less than if you apply that convex combination on the output of the function. So here's a picture. The function in this case is this curve here. The points are going to be x and y here and here. So if I do the convex combination at the input, let's say t is about, I don't know, maybe 0.7 or so, then the convex combination between x and y will put me here. So now I evaluate the function there. That gives me this height. On the other hand, if I look at the outputs, fx and fy, and if I do a convex combination of them, that would get this point, this output. So you can see this output is greater or equal to this one. And so if that happens for all x and y, then you have a convex function. Okay, so you can say it's like convex, or sort of a weighted average at the input should be less than or equal to a weighted average at the output. For all of these weighted averages, where you're weighting somewhere between 0 and 100% of the 2 points. Okay, so is that sort of making sense from a question? Yeah.
Does weighted average can be an like it should be an integer including 0 and 1, or it can be between 0
No, this means the set of real numbers from 0 to 1, everything in between. Yeah. So yeah, it needs to be, it's most interesting when it's in between 0 and 1. Okay, so that's the definition of a convex function. And here's some examples. So these scalar linear functions, those are convex. These functions, we've seen a lot of these linear functions where you take some linear combination of elements within a vector x, add some sort of scalar intercept term. So this function is also convex. Here we have quadratic scalar functions. As long as the coefficient in front of the x squared term is non-negative, that is convex. On the other hand, if a is negative, then you have a concave function, so it's non-convex. Okay, so you can generalize this idea a bit to the same kind of idea works, but for more complicated than quadratic functions. If you look at the second derivative, which in this case would be a, right? But more generally, if you look at the second derivative, and if that exists everywhere, and it's non-negative everywhere, then that function will be convex. Okay, so it's sort of like the intuition is similar to this, but it's more general. Any questions on the ones we've talked about so far? Okay, so if you want to generalize this idea beyond scalar input functions, to vector input functions, what you do is, instead of looking at the second derivative, you look at the Hessian, which is a matrix of all the different second derivatives with respect to the different elements in the vector. And now you need to compare that matrix to 0, so to speak, and that is what is known as positive semi-definite. Positive semi-definite means if I have a matrix, I'll call it H. And for all x, if this condition holds, then that matrix is positive semi-definite. So that's what we need of the Hessian. And that's a property that I was alluding to back in Unit 0 and Unit 1 when I was talking about, like, why when we did linear regression, could we just set the gradient to 0, solve for it, and know that it works? It's because we had this quadratic, multivariate quadratic function, and essentially we could apply this rule to it, and this would turn out to be true. So that's kind of explaining that. Any questions on that one? Okay. So what about norms? Norms are convex. No matter the norm, whether it's a 1 norm, 2 norm, p norm. If f and g are convex functions, so is their sum. It almost works for composition. So if f and g are convex and if f is non-decreasing, then their composition is also convex. And in terms of other examples, RSS, all the varieties of logistic loss like binary cross entropy, regular multinomial cross entropy, all those are convex. And when you add L1 to them, by this rule and this convexity, that's convex. Or when you add L2, that's convex. So all the things we've optimized until now in the course, they've all been convex. So in the case of RSS, we could solve it analytically. But you could also apply Armijo rule or gradient descent, and you could solve it that way if you wanted. And now for logistic regression, multinomial logistic regression, lasso, all those things, they're convex, so they can be optimized tractably. So one issue, though, with the L1 loss is, I think we'll get to this soon. The problem with the L1 loss, though, is it makes the cost non-differentiable, so then these gradient methods don't work anymore. So you have to use more sophisticated methods. But L2 is fine, and RSS and logistic loss, those are differentiable. So it's only when you bring in L1 that those complications arise. Okay, so that's convexity. And this is kind of the final. The reason we care about convex is if f is convex and if x is a local minimizer, then it's also a global minimizer. So the great thing is you can apply gradient descent, which we know converges to local minima. You can apply that to a convex function, and you can know that you're going to get a global minima out of it. So that's why we care about it. Okay. All right. So that's all I have to say about convexity. Are there any questions about convexity? Okay. All right, so let's talk about a couple other optimization topics. Constrained optimization. This is something we haven't seen yet, but it is something we will see in the next unit. So until now, we've had no constraints on our design variables, but you could have constraints such that maybe you need that the sum of all the W terms is equal to 0, for example. It doesn't show up in anything we've seen so far, but you can imagine a problem where that's the case, or some linear combination of them equals some value. So in that case, you can always express it using some function of W equals 0. And in fact, you could have several of these equality constraints. So you could have H1, H2, and so on. These problems show up pretty frequently. So in addition to those equality constraints, you could also have inequality constraints on the parameters W. They could be on some combination of W's or on individual W's or whatever. Just some function of those should be less than or equal to 0. So one question then is, well, what do you do in this case? It seems really complicated. So conveniently, there are some relatively simple, or let's say straightforward methods of handling this. So what you can do is you can reformulate this constrained problem as an unconstrained problem that has some additional design variables. So first, in the case of equality constraints, it's actually pretty straightforward. This is what you do. So you take your original cost and you add this extra term. Here are your linear equality constraints, and you multiply them by these new variables, lambda L. So you need a separate lambda for each one of these constraints you have. And this gives you a new cost function. We can call it L, and it's a function of both W and all these lambdas that we've introduced. Now, you just treat this as an unconstrained problem. You solve it using gradient descent or Miho rule or whatever you want, and you jointly optimize over both of these, and you, in doing so, will automatically satisfy these equality constraints. So let me try to explain the intuition of why that is. So remember that, when we minimize something and we found a minimizer or minima, we know that at the location of that minimizer, the gradient is 0, right? So that means since I've minimized over the lambdas, the gradient of this with respect to each lambda is 0. Well, what is the gradient of that with respect to the first lambda? It's very easy, right? It's just the first h, right? So I know that that equals 0. That's exactly my equality constraint. So setting this up and just knowing the fact that at the optimal solution, the fact that the gradients are equal 0 means that these HWs are automatically also 0. So that is how you're enforcing these constraints. Very straightforward. Okay. In the case you have inequality constraints, it's similar. You add, in addition to your Lagrange multipliers, that's what these lambdas are called. In addition to those, you add some other terms we'll call mu, and they multiply these inequality constraints. And you do a minimization over these, although there's a few extra things you have to check to find what's the solution. It involves something called the KKT conditions. Those are out of the scope of this course. I'll just mention them, but we're not going to get into them at all. But it is what happens. So you can, in a sort of straightforward way, attack inequality constrained problems also as unconstrained problems using this this framework. So it's basically the way these problems are solved. It's pretty convenient. Okay, and I'm mentioning this because we will see this equality constraint stuff show up in the next unit. Okay, so that's it for constrained optimization. Just wanted to mention it briefly. And let me talk about some things that we will not cover. So until now, we've focused on step sizes where essentially we're using the same step size for every one of our variables, right? All the gradient terms get multiplied by the same alpha. The alpha might change over iterations, but it's the same for all the gradient variables. You can imagine generalizing that to where different dimensions use different alphas. But you could even go further and say, well, what if I make alpha an entire matrix? So it's like the multiplying by alpha is like a matrix multiply. Then you can do really sophisticated things. And that is essentially what happens when you do Newton's method. Essentially, you are coming up with an optimal matrix value alpha at every iteration. And what it does is sort of locally approximates the function as quadratic, and then it figures out, okay, if it was quadratic, there's a matrix step size that will take you to the solution in one step. So that means that if you're solving an actual quadratic problem, Newton's method converges in one step. But if you solve some non-quadratic problem, it's going to take longer because it keeps doing quadratic approximations, none of them perfect. But it converges very quickly. Now, although it converges quickly in a few steps, each step is much more complicated because you have to compute this, this whole matrix. You have to do all this extra stuff. So it's very few steps, but very expensive steps. So it's not used that often, but it's sometimes out there. And there's various approximations of it that save computation called quasi-Newton methods. So this is a topic I think that's interesting that you'll see discussed. Another important topic for us, especially when we talk about lasso, is what do you do when you can't compute derivatives? So now you have to use some other method that's not based on derivatives, and there are these methods. We won't get into them. Another point is that all the fancy stuff we did with Armijo, what's nice about it is that it guarantees that when you're in this local minima, it really will get to the bottom of it. But the trouble is, if you have a non-convex cost and you're over here and you're doing Armijo, you will definitely get down here, but you don't want to be there, you want to be over here. So Armijo is a great thing when you have a convex cost function, but when you have a non-convex cost function, you don't want to use it. You want to do something more sophisticated, maybe something that takes such a large step that it will actually bounce you out of this local minima and into the global one. So, or maybe what you want to do is something where as you're moving, there's a sort of momentum and you just keep moving past this shallow local minima and into this deep one. So those are typical tricks that are used with optimization functions for non-convex problems. We'll talk about them briefly when we get to neural networks. But there's a lot of really important stuff we'll not talk about. So we have some good classes on this though. So 5500, Intro to Optimization, is a great course. It's taught every autumn. 6500 focuses more on convex optimization. That is taught the spring of odd years. And there's even a course on non-convex optimization for machine learning, which is taught autumn, even years. So this one should run next autumn. This one should run, let's see. I think it ran this spring. So it won't be taught for another year and a half. But sometimes people ask me, like, what are good courses to take after this if you're interested in machine learning? I definitely recommend all these. Okay. So that's all I have for today. We can end class a little bit early. Any questions on anything here? All right. See you guys on Friday.